n-order polynomial that looks something like this. Maybe we can call it M. Okay, I think the book uses M. Okay, uses M. And then B1Sn minus 1 plus dot 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 plus Bn. So this is an nth order polynomial. And then the numerator and the denominator can also be written as a polynomial. It can be written as Sn plus A1 Sn minus 1 plus dot 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 plus An. Okay, plus An and so on. So this is an nth order polynomial. Okay. So the thing to note here is that when we have the transfer function being written that way, it actually is the ratio of the output versus that of the input. Okay, so if you multiply this out, we can also write this relationship as Bs times f hat of s equal to Ps times y hat of s. Okay? And if you write this out in terms of polynomials again, okay, so you actually have something like B0 Sm plus B1 Sm minus 1 plus dot 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 plus Bm times f hat of s equals Sn plus A1 Sn minus 1 plus dot 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 plus An y hat of s. But what do we know? This thing is Sm times f hat of s. What is this thing? If we were to Fourier transform back to the time domain, what do we have? Sm is equal to, yes, Emmanuel? Okay, what about Nancy? You were chatting, right? I saw you chatting, right? So what is the Fourier Laplace inverse transform of that? You forgot. Okay. What about Larry?
Wait, which Larry?
This is Lawrence. Lawrence. This is Larry. Okay, Larry Resnick, Lawrence, and so on. Okay. So what does this Fourier Laplace inverse transform to? So S Laplace inverse transform to d dt, right? Is what we learned. So this would Laplace inverse transform to dm dt m f of t. Okay? So we can actually take this equation back to the time domain and write it as b0 d dt, or maybe I can write it as dm dtm plus b1 dm minus 1 dtm minus 1 plus dot 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 plus bm f of t being equal to, on the right hand side, I can write it as d dt n plus a1 d dt n minus 1 plus dot 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 plus an times y of t. Okay, so I can convert this relationship between the output and the input into an ODE relationship. And you have seen this kind of ODEs before. So this is the input usually. In our course, this is called the output. Okay, in this course. And then if there's no input, if we are looking for the zero input response, then we set f of t to 0. Okay, this is zero input response. Then we have this equation, 0 is equal to dn dtn, and then plus that thing on the right hand side. And this is similar to what you have learned before. The auxiliary equation, and what kind of solution do you get out of this equation? We learned that in the earlier part of the course when we did ODEs. Exponentials could be. Right? Right. So, remember that we had this equation that we learned in the course, maybe something like a1 d squared dt squared yt plus a2 dt of y t plus a3 y of t. And then it was driven by some right hand side, but if we set the driving term to 0, we find solution to this equation. What is the kind of solution that we call for this equation? The homogeneous solution. The homogeneous solution. Okay. So this will give rise to homogeneous solution. And then the homogeneous solution can be found by assuming that yt is something of the exponential form. If I don't know if you recall something like this. If yt is assumed to be an exponential form like at times a constant, then we plug this in that, we get a polynomial equation. We call the polynomial equation the characteristic equation. Okay, and that polynomial equation is exactly the same as this equation. Okay, so if we set this to 0, that actually was something that we have learned in the beginning of the course. So if we set Sn plus a1 Sn minus 1 plus dot 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 plus an equal to 0, this actually gives you the characteristic equation for finding the homogeneous solution. Okay, so this is the characteristic equation. Okay, and sometimes called the characteristic polynomial. Okay, and sometimes the solutions that you found are called the characteristic modes or characteristic modes. Okay, so in order to find the characteristic modes of the system, we actually set P of S to 0. P of S equal to 0 gives you the characteristic equation. Okay, very much like the first time when we encountered ODEs. We went through the same exercise, but we did nothing higher order than second order. You obtain the characteristic equations, and then you can actually now look at this system and say that that characteristic equation is just by setting the denominator of the polynomial equation to 0 over there. Okay. And then of course you can factorize this polynomial. This polynomial can be factorized. You can write as s minus s1, s minus s2, s minus s3, and then s minus sn. And then after you factorize them, you can find all the roots of that polynomial. And then all the roots of the polynomial gives you the characteristic modes. The characteristic modes. And then you can say that the homogeneous solution of this system is actually equal to A1 e to the S1t plus A2. Maybe I shouldn't use A. Maybe I should use C1. C2 e to the S2t plus C3 e to the S3t plus dot 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 plus Cn e to the Snt. Okay? So these are called the characteristic modes of the equation. Very much like what we did earlier in the course where we found the homogeneous solutions. And then we find these characteristic modes and characteristic equations differently here. Okay? And how would we find those coefficients C1, C2, and C3? What did we do in the beginning of the course when we were solving this equation in the time domain? We use initial condition. We use the initial condition in order to find those constants. Okay, so we maybe say y0 minus is equal to something, y prime 0 minus is equal to something, and then by doing that, you can find out the constants that we want. You will do the same thing here. You will use the initial condition to find those constants. Okay. So are there any questions regarding this? This is rather confusing, but this is how you find the characteristic modes and the characteristic polynomial and the characteristic equations of the system. You found that by just setting the denominator to 0 at the poles of the system. Okay?